Hello viewers, this is Wagadaruna taking you through today's tutorial on how to express a complex number in Modulus-Argument form. So consider a complex number a plus bi whose Argand diagram is as shown below. So in the previous lesson you learned how to draw an Argand diagram. So this complex number, the Argand real part is a and imaginary part is b. So from the Argand diagram, remember this is a right angle triangle, we can know that cos theta is this is theta, so cos will be adjacent over hypotenuse, which is a over r. When you make a the subject, you shall come up with r cos theta. On the other hand, sin theta opposite over adjacent over hypotenuse, which is b over r. So when you make b the subject, you shall come up with r sin theta, where r is the modulus of z. So r, you can also denote modulus of a complex number. So substituting for a and b in z, we shall come up with r cos theta plus r sin theta I. In that, r is common, so if we factorize it out, we shall come up with cos theta plus I sin theta in brackets, and thus that will be r. So this is the Modulus-Argument form of a complex number. Modulus meaning magnitude, and argument meaning the angle, and we shall use that to come up with some formulas for multiplication and division arithmetic. So multiplication of complex numbers in Modulus-Argument form. So if z1 is given by that and z2 is given by this, then when you apply the two, it means you should say that times that to give you this. In that case, when you collect like terms, modulus this times this can be brought together to give that, so that you remain with the arguments cos and sin. After that, you shall now expand, open brackets, so this times this to give you that, then this times this to give you this times this to give you that, and this times this to give you that. So the minus is from the I squared. Remember, I and I gives I squared, which is -1, so we get minus here. So in that case, we shall rearrange, collect like terms, real alone, imaginary alone. So real is this, and imaginary is that. So when you look at this real part, it can be simplified to cos theta 1 plus theta 2. And the imaginary part can be simplified to sin theta 1 plus theta 2. So in conclusion, it means that when you multiply, when two vectors are so from this we shall come up with a conclusion that when two complex numbers are multiplied, their modulus is the modulus of each independent complex number, and multiply them. Just as here, so modulus of z1 z2 is equal to modulus of z1 times modulus of z2, and comes from this expression r1 r2. For the argument, when you look at this, it is a sum. So argument of the product of two complex numbers is the sum of the argument of the independent complex numbers. So argument of z1 times z2 is equal to argument of z1 alone plus argument of z2 alone. What about division? So for division, if z1 is that and z2 is that, we shall divide z1 over z2 to get that, and here we shall multiply up and down by the conjugate, so that we remove this imaginary part from the denominator. So multiply by the conjugate of the denominator, which is that up and down. All that we shall open brackets, down it will be, this is difference of two squares, so it will be that for up we shall multiply this times this times that, plus this times that, and this times that. So you shall come up with this line, and you can simplify it further by collecting like terms, real alone and imaginary alone. So when you look at the real part, it will be equal to cos theta 1 minus theta 2, and the imaginary part, it will be equal to sin theta 1 minus theta 2. But outside, the modular is the division R1 over R2. So what does that imply? It means that modulus of Z1 over Z2 is equal to modulus of Z1 alone divided by modulus of Z2 alone. But for the argument of Z1 over Z2 is equal to argument of Z1 alone minus argument of Z2 alone. So we shall use those concepts to come up with the solutions to these problems. Problem 1. Given that Z1 is equal to 2 minus 3i, and Z2 is equal to negative 2 plus 5i, represent Z1 and Z2 on the Argand diagram, and hence find Roman 1 modulus of Z1 Z2, Roman 2 argument of Z1 Z2, Roman 3 modulus of Z1 over Z2, and Roman 4 argument of Z1 over Z2. For the Argand diagram, for Z1, positive real, negative imaginary, positive real, negative imaginary. So that will be the the Argand diagram for Z1. For Z2, negative real, positive imaginary, negative real, positive imaginary. So that will be the Argand diagram for Z2. Then we shall get their modulus, independent modulus. For Z1 to be 2 squared plus 3 squared, everything under root, to get root 13. Z2 to be 2 squared plus 5 squared, everything under root, to get root 29. Then the argument of Z1, it will be a negative value because it's going in the clockwise direction. So negative arctan 3 over 2 to give you negative 56.31. For Z2 to be a positive because going in the anti-clockwise direction. So positive 180 minus theta 2, which is 180 minus arctan 5 over 2, which gives you 111.8. Now that we have got the independent moduli and arguments, we can come up with the solutions. So modulus of the product of Z1 and Z2 will be equal to the product of the modulus of Z1 alone times modulus of Z2 alone, which is root 13 times root 29, and to give you root 377 as our answer. For the argument, we have to add. We say product here, we add here. So argument of Z1 was negative 56.31, Z2 was 111.8. So when you add, you get 55.49 degrees. Then for the division, we have to divide the independent moduli. So root 13 over root 29 will give you 0.6695. For the argument, we subtract, so this minus that to give you negative. So it has to be negative 168.11. So that brings us to the end of our lesson. Thank you for watching. I remain Wagada Ronald, and please subscribe to my channel, Rowa e-learning platform. Thank you.